welcome to Module 26, Linear Dimensionality Reduction and Principal Components Analysis, or PCA. By the end of this module, you should be able to explain what linear dimensionality reduction is and when PCA is an appropriate tool. You'll be able to define principal components in terms of variance, maximization, and reconstruction error, at least at a theoretical level. You'll be able to derive or follow the optimization problem whose solution gives PCA directions as eigenvectors of the covariance matrix, again, at least theoretically. You'll be able to implement PCA in Python with and without the scikit-learn library, and you'll be able to interpret explained variance ratios. And finally, you'll be able to evaluate the impact of PCA on downstream tasks like classification and tell whether or not it helps or hurts. So, in the past, I've sometimes framed the idea of reducing data or throwing data away as not being optimal. Even if you have a majority class classification problem, the solution is oversampling the minority class, not downsampling the majority class. This is a somewhat different problem, though. Normally, when we're talking about dimensionality reduction, we're doing so because we have limited computation. Maybe we're trying to deploy a model on a platform which is very low power, very low memory. Models will get too slow or wouldn't even fit, so optimization becomes an issue. Maybe you have way too many features, way too few samples, and that's one of the situations in which a model might overfit. It could memorize the noise that's kind of emphasized in this small sample size, and we want to maybe reduce features that kind of convey that noise. Sometimes we want to use it as a form of visualization. So we're going to often plot our results or our clusters or whatever the case may be. And humans who are going to be looking at these graphs, we're good in 2 dimensions, maybe 3 dimensions, but anything beyond that is very difficult for humans to evaluate. So if we have multi-dimensional data, boiling things down to 2 or 3 dimensions can help. And occasionally, features, or especially highly correlated pairs of features, are basically duplicated. It's a waste of time. It causes basically a lot of problems of the type we've been talking about just now. I mean, removing those columns is one way to solve the problem, but reducing dimensionality kind of in terms of the data itself is usually the solution. So this involves taking data X, which is d-dimensional real data, and converting it to a data vector Z, which is k-dimensional real value data, where k is much, much smaller than d. Maybe maybe the original cardinality of your data, the original dimensionality of your data is d equals 100. You want to squish things down into k equals 5 or 6 dimensions. But you want to make sure that the important structure is retained, right? So again, machine learning and modeling is all about finding the needle in the haystack, finding the signal among the noise. You don't want to make things, there's an expression, keep things as simple as possible, but not simpler. Same thing happens here. You don't want to, compress or filter everything down and then end up losing the thing you actually care about. So principal components analysis, PCA, is the canonical gateway linear method for doing this dimensionality reduction, which we'll write as DR most of the time. So let's scaffold our concepts. We assume that we have a big data matrix X of n examples and d features. And let's for now imagine that the d is centered. So every element of the d dimensions has 0 mean. And we can do that, say, by Z scoring. So linear dimensionality reduction means choosing some matrix W, which is a d by k matrix. So the same dimensionality, like the number of rows is the same as the number of columns in X. And k is the number of dimensions we want to have when we transform our data. And basically what we want to do is just do this linear operation. We want to take their data matrix X, multiply it by W in a way that makes sense, because all the linear algebra stuff, the dimensionalities match up. And then we want to get this low dimensional representation, which is going to end up through this multiplication being an n by k matrix. We'll still have 1 row for every data element, but the width of those rows, the number of variables will be k, which is small. We've compressed things by multiplying X through some optimum matrix W. And then if we want to, we can reconstruct the data, as closely as possible. So if we take Z and then multiply it by the transpose of W, we should get some new matrix X hat, which is as close to X as possible, right? This kind of touches on the retaining the important signal idea. If we squish the data down to k dimensions, we want to be able to get it back in the end. This is a little bit like, lossy compression, kind of. But this is extremely simple. So the main thing comes in, like, how do we actually choose the good directions W? How do we actually choose W that's appropriate? And what does good even mean? So let's think about projection in this little example here. On the left, we have this two-dimensional cloud of original points in blue. And we have something I'm calling a principal component, or PC1, which is this this orange kind of line over here, or this actually the orange line are the projections, but it's basically this line defined by these orange dots over here. Now the principal component here is a sort of like a dimension, like in this space of points, which carries most of the change that I'm observing in the data. So looking at these data points, most of the variance, if you tilt your head a little bit, most of the variance happens in this direction, which is demonstrated by this dimension principal component 1. And so I define that. That's just my first dimension. And now I can take all of my individual data points and I can project them down like at a right angle to that line. And whatever the point lines in that line, that's the representation of the data. It might be hard to see in the video, but on the slides you can see that, well, this point over here has this orange line kind of sticking out from it and going straight down towards this principal component at a right angle. So I've converted this two-dimensional dot in feature 1, feature 2 space, 2 dimensions. I've projected it down onto principal component 1, and wherever it falls on this line is now only 1 dimension. It's one number, which says how far to the left on PC1 am I, or how far to the right on PC1 am I. I have reduced d dimensions, which d equals 2, to k dimensions, k equals 1. Not a huge necessarily compression, but it's something. This is the rotated view I was talking about a moment ago. So I found PC1, I rotate all the data, and then I obtain this graph on the right. And now you can see the projection of each of these dots onto this horizontal line now is the projection of the data onto into this lower dimensional space, PC1. So PCA in one sentence basically means finding orthogonal directions in feature space. Orthogonal just means like vectors that are right angles to each other in whatever the space is. I want to choose these directions one by one so that I'm capturing as much of the variance as possible. In this example, most of the variance occurred along this dimension, which is shown here as PC1. The second one is, the second directions are orthogonal to PC1. There's only one direction that's orthogonal to PC1, and given that I have only 2 dimensions, that's this next dimension over here, and I'm kind of done already. But if you have like hundreds of dimensions, well, I'll show you in a second with 3 dimensions, you have a choice. So yeah, the first principal component is the overall direction where the projected data has maximum variance, and then you subsequently maximize the variance as long as you're orthogonal to the earlier dimensions. So here's something that demonstrates that in a somewhat less constrained 3 dimensions. Again, play around with this on your own. Now the gray dots are in 3 dimensions. And the red line here is the first principal component. Most of the variation occurs along this axis. So I found PC1. Can I turn them off? Yeah, I can turn them off. So I found PC1, this red dimension. But now looking at the barrel here kind of thing, looking at PC1, now I have another 2-dimensional cloud of data, right? So which direction here has the most amount of variance in it? Well, it's actually this one, right? So the visualization here is a bit off a little bit, but most of the variation in these 2 dimensions happened along that green line indicated here. I could have chosen all of them. So you can imagine like this green line can kind of rotate around the red PC1 axis. I have like an infinite number of possible second principal components, but given that PC1 is here and I projected the data in this manner, this is the direction that has the maximum amount of variance. And then PC3 is the only one that's left over here. PC3 is orthogonal to both PC1 and PC2. And that's basically it. So the anti-example. So occasionally we use PCA as a pre-processing step. I have too many features. I want to project them down into a smaller number of dimensions. I should mention one more thing here, actually. So here, feature 1, feature 2, feature 3, these are meaningless. Principal components 1, 2, and 3 are also meaningless. Usually the input features might be having actual units, like age, income, number of visits, and so on. These are in terms of years, dollars, counts, and so on. But when I take a principal component and I've kind of combined each of these three dimensions in order to define each of my principal components, now the units of measurement are lost. The units of measurement are some kind of weird linear combination of years, dollars, counts, and binary labels. So principal component 1, 2, and 3 don't have units of measure, and if they did, they're on different scales. You can't take principal component 1 and treat it as if it's just another feature. You have to remember that it's an aggregate of different measures. Regardless, initially I have a couple of different measurements: age in years, income in dollars, number of visits as counts. So a problematic root workflow, which I've seen happen, is this. You take all of the data, you're doing pre-processing mode, so I haven't gone to training yet, so I don't care about training or validation or test. I'm going to take all of my data, I'm going to clean all of it. I'm going to, removing outliers, is another thing where, that can involve a bit of pseudo modeling, and you do that on the training set only and then do it on the test set. Other forms of pre-processing might be, just removing entries that are empty. And in that case, you could do that before you do training and testing technically, but it's not good practice. And certainly this example is bad, right? So if I take all of my training, validation, and test data and fit a principal components analysis on all of it, so some of these gray dots are training, some of them are testing. Like you can imagine removing some of these gray dots because it's test set. Now the directions of maximum variance will be slightly different. So my principal components are now different than they would have been if I kept those data points in. So I have an influence of the test set on my model that I'm going to be using on my training set. Like my principal components during training are going to depend on information I had in the test set. I transform everything with PCA, and then I go ahead and start training a model. Well, these directions of PCA are informed by your test set, and even if I didn't use any labels in the test set, this is still a form of data leakage, right? So it's a bit more complicated than this, not too much more complicated than this, but I invite you to just think about it and think about what went wrong and think about how you might go about solving this problem. So here's a bit of the answer. The PCA can see the test set during fitting. It learns the directions optimized, including future examples. And then the evaluation is optimistically biased. This is a form of data leakage, like I mentioned a moment ago. This representation is tuned on information from the test set. What can a fix be? Think about that for a bit. So you can, first of all, only fit the PCA on the training data. And then once you've done that, you can take the learned transformation and then apply it to the validation and test. So, learn the directions of PC1, PC2, and PC3 on the training data. Don't learn a whole new transformation on the test. Take the same directions, PC1, PC2, PC3, take the new test data and then, adjust them according to the principal components. That's the way to do it. In scikit-learn, you might practically wrap PCA inside of a pipeline so that any kind of fit or transformation happen within the correct splits. So the kind of fictional situation I mentioned a moment ago wouldn't happen because everything's in a pipeline and everything's bifurcated and separated for you appropriately. So practically you use pipeline, and you'd also, again, maybe think about this a bit. Like I jumped very quickly through this. Like I would have liked you to pause the video and think about it and jot down some of your answers to these questions beforehand. But regardless, time is of the essence. So now something for you to consider though is like why, I just mentioned, we obtain the principal components on just the training data and we don't use those directions on the test data. Why would we not do another principal components analysis on the test data and then transform the test data to its version of PC1, PC2, and PC3, and then do our evaluation on test set using a model learned on a PCA transformation of the training data set? Like, why wouldn't you do that? Why are we using one principal components analysis trained only on the training data and using that same representation to reduce the dimensionality of our test data? Why would we do that? And what kind of problems would occur if we didn't? Great, math mode. let's make the setup for PCA precise. We'll think of our data set as a matrix X. Every row is one example. Every column is a feature. As usual, we have n points, and D is the dimension of our feature space. The first thing to do is to compute the sample mean. So this is just the, we're just averaging over all of the n examples, and then we end up with a d-dimensional sample mean vector mu. Then we build a centered data matrix. So if you can imagine our original data X, we're just going to subtract the mean from each of the dimensions. Again, mu is a d-dimensional vector, so we're just going to subtract the mean from every row. And this means basically every feature, every column will now have a mean of 0. So we kind of centered our big cloud of data around 0. Centering is going to be important. So PCA is about variation around the mean. So if we don't center, then the mean can dominate what we're going to call variance, and we don't want that. So this is an important step. Then we sample the covariance matrix. So for the centered data, we need to compute, the sample covariance matrix. This is a square matrix. This is a D by D matrix. So element-wise, J sub k is the average product of x sub ij minus mu j times x sub ik minus mu k. So it basically measures how features j and k covary across the data set. So it's like, it's d-dimensional by d-dimensional. Element I, ij refers to how much I and j covary with each other. So this is nothing, this is kind of a standard representation. I wouldn't expect you to memorize this particular equation. Most people kind of don't, but just high level, what is the covariance matrix big sigma? We understand that two variables can have covariance with each other, and all those different covariances are just represented in this big matrix, and obviously it's symmetric, right? So the covariance of ij is the same as the covariance of ji, so it's symmetric along the diagonal. So many textbooks divide by n-1 instead of n here, but because n-1 is what we use for samples and n is what we use for populations, and technically we have samples here, we're not overall populations. This is a bit of splitting hairs, and some texts won't make this distinction because they don't care or they don't know. For now, we're going to not care to the extent to which we don't need to care, because for PCA, this is only going to rescale eigenvalues, not directions. So it doesn't really change the principal components. That's kind of a glib way of brushing it aside, but if you really want, I can provide you some texts to kind of make this a bit clearer. Next, for any, if you were to pick any unit vector, so W is d-dimensional and its 2 norm is 1, so it's a vector of length 1. You can think of this as just a direction in feature space. Often these unit vectors are used just to define, it's a vector in space and it points in a particular direction. If you were to project every centered point, so all my data has been centered now because I've subtracted the mean, and I want to project each centered point on the direction described by this unit vector W, then the scalar coordinate, by definition, is just going to be the transpose of W times the shifted data point. So x sub I minus mu is what I called Z somewhere, I think. Maybe on the next slide. But yeah, so this, here it is. I'm literally looking at it as I'm searching for it. Z sub I is sort of the projection. It's a scalar coordinate of x along the direction of W. And sorry, the x with its mean removed. So I've already taken care of removing the mean. So therefore, we know kind of how far along the direction W this random shifted data point is at this point. Now, if you wanted the actual point back in d dimensions that lied on the space, on the line spanned by W, you can still reconstruct it. So you could project down into this direction, which is sort of like removing dimensionality. But then if you're like, well, I want to make sure this direction is a good representation of my data. I want to be able to reconstruct my data in a way that is as close to the truth as possible, as close to the original as possible. Then I can kind of do the inverse, or the reverse, I guess. I can take the mean and I can add z sub I multiplied by w. This is going to give me x sub I hat, which is sort of the projection. So like x sub I hat being the orthogonal projection of xi onto the line through the mean is what I obtain. And finally, the variance of the projected data. This is kind of the big thing. This is sort of the engine that's going to let us compute all of our directions w. If you look at the variance of all of these scalar coordinates z sub I that have been converted, it's nice. It's a nice fact that if you go through the steps of computing the variance of what we just defined a moment ago here of z sub I, this is going to be just our directions w times the original covariance matrix from over here times, again, the unit vector w. So if I choose a direction w, I have a choice of which direction can be my first principal component. Bit of a spoiler alert. I'm going to choose w to be a really good representation of the data. I can compute the variance of the data along that direction just by this simple quadratic form, w transpose times big sigma times w. And this is the key thing. So the covariance matrix big sigma plus the direction w will tell me tell us how spread out the data is along w. And if I can choose a good w, and I'll do this using PCA, good being good representations of the data, then I'll be able to reconstruct the data really accurately. So I want to choose directions that capture most of the change. I want to choose a direction of w where the variance is as large as possible. I brushed over this a moment ago, but that's essentially what I'm doing here. So now that we know that we can measure variance along these directions w, we can finally define what PCA is actually doing, because I actually want to find a w. So the first principal component, and again, I showed graphs of what I'm looking for earlier. The first principal component is like I want to find, out of all the possible unit vector directions w, which one will give me the biggest variance when I project the data onto it. So in math, that's just this thing over here. So that's just like find a direction w sub 1 that maximizes this projected variance, subject to the mere condition that my w sub 1 is a unit vector, just for simplicity. So Lagrangian multipliers are a little bit outside of the scope of this class, in terms of like high-level concepts, but I'd encourage you to just click on this and read a little bit more about it if it's unfamiliar to you. This is a constrained optimization problem, and then therefore we can use these things called Lagrangian multipliers to handle the constraint. You might have seen these in your like algebra classes. It comes up in algebra and it comes up in calculus also, multivariate calculus. You've probably seen it pretty abstractly, but now, we're going to use it as an off-the-shelf tool at the moment. So we have the Lagrangian of direction w sub 1, and we have lambda. So lambda is this term that will just penalize deviations from the unit length constraint. Like we've seen these hyperparameters that allow us to have a little bit of wiggle room. Lambda is the wiggle room we have within the Lagrangian. So the Lagrangian is just this thing we're trying to maximize minus lambda times this constraint that we have a unit vector. This is very similar to what we saw with a soft margin in support vector machines. We had like the first term was the main thing we're trying to optimize, but then we had this kind of slack term, which also had a hyperparameter on it, which says, yeah, well, you still, you have this little bit of weight for this extra thing, which we want to maintain, but if you can't maintain it perfectly, that's okay. That's what we get from this second term. Anyway, this isn't a loss function. I know it's a squiggly looking L. It's an unfortunate thing that there's only so many letters of the Greek alphabet and the Latin alphabet that allow us to represent all these different concepts. This is not a loss. It's not an empirical risk. This is the Lagrangian that we're going to just optimize directly. So like we've seen previously in actually in iterative methods, if we set this this Lagrangian to 0 and then solve, we can do a few things. So this is this is the equation. I mean, I'm skipping a lot of steps here. It's not that important. This is under the microscope again. If you really care to, you can go about and do this exercise on your own. But the gradient is this. Setting it to 0 allows us to solve for W. So big sigma is the big covariance matrix. Lambda is our actually lambda is our eigenvalue now. This is getting a little bit in the weeds a little bit. You might remember the idea of eigenvalues and eigenvectors. Like a matrix A can be represented as a combination of these things called eigenvectors multiplied by eigenvalues. This lambda is just the eigenvalue. So again, this might be digging into the past, into your history with some of the pre-existing math that not all of you might have seen extremely recently. For those who know what an eigenvector is, W sub 1 must be the one of the eigenvectors of the covariance matrix big sigma. For everyone, including people who don't necessarily remember what eigenvectors are and eigenvalues, W sub 1 is just maximizing the variance corresponding to the largest eigenvalue. Eigenvalues are essentially like scalars that define the extent to which these eigenvectors are used to represent some original matrix. The biggest eigenvalue, this is like the biggest, here in this case, it's the biggest amount of variance we have in our, the biggest amount of influence the first eigenvector has on, or the large eigenvector associated with this largest eigenvalue has on sigma squared. Very, very simply, we have a lot of eigenvalues. The biggest one represents, is associated with the first eigenvector, and that eigenvector is going to be our first principal component, and all of these ideas together just means that eigenvector is going to be pointing in the direction with the largest variance, because we're working with the covariance matrix here. Hopefully that makes sense. I dug into some of your pasts in a bit of a way with regards to eigenvectors and Lagrange multipliers. But I think big picture, again, hopefully the main story is not being lost here. If you have to go back to the visualization we had before, that might help a little bit. We have a big cloud of data. There's some direction within this big cloud of data in which the data is changing maximally. That is represented here by W sub 1. This is our first principal component, PC1, and that happens to be an eigenvector. That first case has the eigenvector with the highest eigenvalue for those who know what that means or care to remember it. I'm almost certainly not going to ask you about eigenvectors or eigenvalues on the exams. So that's how we pick the first principal component, W sub 1. Now we need to look at the second direction, W sub 2 and W sub 3, and any ones we can subsequently find. We still want to maximize variance. We want to find W sub 2 that maximizes the remaining variance. It has to be orthogonal to W sub 1, so we're again trying to solve this constrained optimization. We're trying to find a W sub 2 that maximizes this equation, subject to the fact that, again, this vector is a unit vector and it's orthogonal. So this multiplication here being 0 just means that they're orthogonal to each other. We talked a little bit about this. Actually, this comes up a lot in basic linear algebra. One vector multiplied by another in this way, having a 0 product, means that they're orthogonal. Or like, they're 90 degrees between them. So again, the same logic as before applies. We're going to skip over it. W sub 2 is going to be the eigenvector corresponding to the second largest eigenvalue of sigma. And then now we have W sub 2, which is another direction. And we can continue in this way until we have found k principal components with the top k eigenvalues. This will give us associated eigenvectors, and those eigenvectors are just the directions of maximum variance within sigma. Okay. Again, eigenvectors and eigenvalues, which scale them, allow you to reconstruct any matrix A. The matrix we're trying to reconstruct now is the covariance matrix in our data, and so we want to see like which direction has the biggest influence, which is the orthonormal one that has the next biggest influence, and so on. Again, we already know how to do this. I'm just kind of getting into the math. Like we already know what I'm doing in a geometric kind of way. Regardless, at the end of this process, and this is like not a process I need to kind of like learn. It's one that has a closed form solution. I have a big matrix, big W sub k, which is eigenvector 1, principal component 1, eigenvector 2, which is principal component 2, and so forth, all the way to my kth principal component. Now I have a d by k matrix, which can take data in d dimensions and convert it into k dimensions by multiplying those together. So specifically, I do that exact same thing here. I have n by d matrix x, or maybe the shifted data, big X. I multiply the n by d matrix by a d by k matrix. This product will be an n by k matrix, which I advertise at the beginning of this module, will give me my transformations of d-dimensional data, where d is massive, into a set of k dimensions, where k is as informative as possible, where informative means representations of maximum variance. Another view of this is just like a rank k approximation of x. This is not really another view. This is really the same view as before. But again, like a reconstruction of x would be my, like, I converted to z. So z is my low dimensional representation. I can reobtain an approximation in my original d-dimensional space by multiplying again by the transpose of w. Everything has the same definition as before. So you can choose like a reconstruction, x hat. X hat has a rank which is less than or equal to k. Again, I might be going into linear algebra a little bit. Again, this is under the microscope, so hopefully you can tell the difference between what is purely super interesting, which is this stuff here, versus what is interesting and necessary for the exam, which might not be this. Regardless, the difference between the original data and the reconstructed data, x hat, I want to choose an x hat such that the difference between the original data and my reconstructed data, according to this 2 norm here, is as small as possible. Specifically, this is the Frobenius norm. This is just a sum of squared entries. So again, it's very similar to like things like L2 norm or Euclidean distance. It's just same basic idea. It's a 2 norm. This is a subset called the Frobenius norm. You can learn more about this here. But big picture, you get the idea. I have a matrix x hat, which can be produced using k or fewer vectors. So its rank is less than or equal to k. And that reconstruction is going to be kind of a lossy representation of the original data x. I want those to be as close as possible. I want to have lost as little information as possible. I want this difference to be as small as possible. So I want to choose x hat to minimize this norm, to minimize this distance. So it turns out that, again, skipping a lot of things here, the solution to this equation is given by zooming out from this camera. And after you've zoomed out in this camera, you use PCA, using the same method we mentioned before of finding the eigenvectors and the eigenvalues. W sub k being the eigenvectors of covariance matrix sigma, corresponding to all this stuff. So like how we define z in such that x hat has a minimum difference from the original data through this Frobenius norm. The solution to this problem is to choose W, which is just the best k eigenvectors corresponding to the top k eigenvalues. So again, going step by step and adding one dimension at a time in order to just choose directions of maximum variance in the data. That was one way to obtain these principal components. The other way to do it was to say, well, I want to be able to boil my data down into a small number of k dimensions. I want to do lossy compression in a certain sense, but then I want to use that compression to reconstruct the original data if I needed to. And I want to make sure I encode as much useful information as possible to make the difference between the original data and the reconstructed data as small as possible, which is this minimization here. And again, skipping the steps that prove this, the proof is that all that work we did step by step a moment ago with principal components analysis is the answer to this. Principal components gives us the best linear compression of the data. Again, this is linear because we're just doing matrix multiplication. In the next module, we're going to see nonlinear transformations of the data. So there's other solutions that are not linear, but if we're just looking at linear transformations of matrices, then the PCA is the solution to our reconstruction error minimization. And that's awesome. So we're choosing like some k-dimensional linear space, and it's going to be the best, through PCA, we're going to find the best k-dimensional linear subspace that will allow us to reconstruct the data in this least squares sense. So this is another bit of a stretch. So far I just went into the math a little bit more to just kind of clarify and specify our intuition about those images we were looking at earlier. Singular value decomposition, or SVD, of a matrix X, this is a data matrix X, can be represented as three matrices, U times sigma sub X times the transpose of V. So U is an n by n orthogonal matrix. These are left singular vectors. V is right singular vectors. This is a d by d matrix. And sigma sub X is going to be a diagonal matrix with sigma sub 1 along the diagonal. It's going to be all zeros, except there's going to be a couple of singular values on the diagonal. Okay, so big picture, I don't think I'm going to talk about this again later, but soon enough we're going to talk about neural networks and embeddings and projections, which is going to touch on a lot of the concepts we're talking about here already. We're taking massive dimensional data and we're projecting it down into a small number of dimensions. The small number of dimensions is in some space that has no units. I mentioned that earlier also. It's not measured in terms of age or income dollars or centimeters or whatever. It's some abstract, hidden, latent dimension, which is just the principal component dimensions. Those dimensions are like embedding dimensions, and U is a way of taking my n data points and projecting those data points down into those smaller k embedding dimensions. V is sort of like taking the dimensions, the original dimensions themselves, the original d dimensions, and projecting them onto the subspace, this k-dimensional subspace. And then sigma is sort of just like a weight matrix in some way, which is still important. But I think U and V is conceptually is also important because it's sort of like, if you want to say this data point, which is very complicated, can be projected into a smaller number of dimensions, that would be encoded within matrix U in this decomposition of X. It's n by n, right? And V would be kind of the other direction. It would be like to what extent is this, like these dimensions relate to one another in this subspace, if that makes sense. We might see this. We might see a version of this later when we come back to embedding vectors in a future module. Regardless, the columns of V are V here on the right are the eigenvectors of the covariance matrix here. And again, this is a bit of detail that I'm not going to ask you to know this. This is stretch. This should be also called aside, but there's something called the Eckart-Young theorem defined or described here. It says that the best rank k approximation of xk in the Frobenius norm, which we were talking about a moment ago, like in terms of the reconstruction error, the best rank k approximation is actually this product of three matrices, U and sigma and V, giving us this like rank k approximation of x sub k here. Here we're only going to keep the top k singular values or vectors. So I'm not taking the entire sigma sub x. I'm only taking the subset, which is like the best ones, like the top k of them. So I don't care about, all of the n by d dimensions. I just kind of boil them down to k. And I'm done. So the PCA directions basically refer to the columns of V. The PCA scores are sort of x times V or U times sigma squared, and these things are all equivalent to one another. So these are all sort of three ways of viewing principal components analysis. One is just the engineering exercise of finding dimensions that maximize the variance one by one. The second interpretation is I want to minimize the distance between my real data and my reconstructed data if I boil things down to k dimensions. That was this version. And then I have this third representation, which is the singular value decomposition, or SVD of x. And through this old theorem, it again shows the same old thing, that The optimized best rank K approximation can be represented in terms of U times sigma K, sigma sub K, which we already know how to get, which is X times V. So 3 views of the same phenomena. I'm kind of repeating myself to some extent, but I think it's still important just to get a little bit deep on some of these things. I'll point out also that occasionally when you look into the source code of these libraries that we're just sort of using in machine learning, you will see that the principal components analysis library is normally, not always, but it's often implemented in terms of singular value decomposition. So like you'll do a singular value decomposition, and then you'll choose your rows and columns from vectors u and v, and then that will essentially give you your principal components and their weights, which you then return from your principal components analysis function. So in practice, again, there's a couple of steps here. This is jumping back to the level that you might be more responsible for. What do? If you have data you have n data points in d dimensions, and you want to boil them down to a small number k dimensions. First, you center the data by computing the mean and subtracting the mean from each feature. Then you will compute the covariance matrix. One of the simplest equations is just taking the x transposed by x and then dividing by n. You won't need to memorize this, but just know that the covariance matrix is sort of what you're looking to find. I mean, technically, next you're going to do an eigendecomposition of the covariance matrix sigma. So an eigendecomposition, again, is just a way of taking a matrix A and representing it as a product of vector lambda, which is a bunch of scalars, and a matrix, which is a bunch of eigenvectors. And then it's a way of just basically finding orthonormal vectors to one another and then scaling them. So you could take any distribution of data you start off with a bunch of unit vectors, and then you rotate it according to the dimensions of the eigenvectors, and then you stretch them according to the amounts of the eigenvalues, and then that will reconstruct any matrix that you have in mind. And in this case, this will give us, through a series of steps, the original data. But anyway, the point of this eigendecomposition is a fancy way of just basically saying, finding your orthonormal directions to each other that maximize the amount of variance. Choose the top k of them. K is some hyperparameter you have, and then given these directions, you just project your original d-dimensional data down onto these k dimensions, and you're done. If you want, you can reconstruct the data. So you can take your projected data, which is k-dimensional data points, and then you can remultiply it by the transpose of this weight matrix W. This will give you a reconstruction, and then you can compute how different the reconstruction is from reality if you want to do like a bit of intrinsic analysis. But normally you stop at 5. You get your projected data. We have removed a lot of the noise, outliers, and extraneous information, and we've kind of kept the core useful information for our data. So there's a link, sklearn decomposition.pca will handle this all for you. So usually you can just kind of blindly use PCA and you're happy and you get your k-dimensional data, but it's still important to know what's happening under the hood, for several reasons, not least of which is the thought experiment we had several slides ago about the anti-example. What can go wrong? If you compute PCA over all of your data, training and test, then that will manipulate the directions of your maximum variance, its linking information, and so on. It's important to know what's happening under the hood. You're not a passive, superficial user of machine learning. You are a well-aware, knowledgeable machine learning expert, and that's what you're trying to accomplish. And you want to learn these things. So this is a bit of a SVD picture. This is a kind of visualization of what I just mentioned a few moments ago. You have a SVD, singular value decomposition of your original data X. So it's U times sigma times V T. So again, U is an n by d dimensional matrix. V is d by d. And sigma is this diagonal matrix. Again, I think I mentioned it a moment ago. The unfortunate thing about a lot of machine learning is there's so many concepts and there's only so many letters of even 2 alphabets, Latin and Greek. So now, like before, big sigma was our big covariance matrix, and now Big sigma is our diagonal of our singular values, sigma sub 1 all the way to sigma sub d. So don't get that confused. So conceptually, this is what it looks like. So before, when it was just symbols, it was maybe hard to grasp what's going on. Here's a visualization of what I was talking about. So our data matrix X can be decomposed unambiguously into these three matrices. And if I wanted, so it's like my d dimensions, projected onto my singular values, and then this product multiplied by v will give me my original X. If I wanted to embed, my d-dimensional data, here's my n rows of data representing my n data points. I can just literally cut off the first k columns. Those are my embeddings of my first of my n data points, the projections of those onto k dimensions. The sigmas are normally that important for you as a machine learning person. Usually all you care about is these embeddings. But sigmas can actually scale things in a way that's appropriate. Occasionally it's good for reporting, so I'm not to say to throw these things away or anything, but embeddings are kind of what we're looking for. And then v's over here are basically just describing the relationships of the data with itself. So anyway, to form the best rank k approximation, so an approximation of the data with rank k, you can drop all of the gray parts and keep only the top k parts. So I take the first k columns of u, I take the first k elements along the diagonal of sigma, and I can take the first k rows of v, which are going to be columns of v transpose. And then if I multiply just those things together, just the first k columns, the first k elements, the first k rows, I get this approximation x sub k. This is the best approximation of my original data by using only the best k dimensions, again linearly. This can all boil down to this representation also, the same idea. This is nothing new, we've talked about this already before. This is just a way of visualizing what's going on inside of these matrices when I'm taking my representation of all of the data, which is all of this, and then boiling it down to just k dimensions, which is just the red parts. So a few examples here. So this is where I guess the main, where the rubber hits the road, so to speak. So here's a little kind of fictional example again. We've produced this data according to multivariate normal distributions here. So it's an old familiar cloud of data kind of stretching out obviously in one direction. So here's just a raw, it's correlated two-dimensional data in two features that might have units of meaning that we don't encode at the moment. So literally, I mentioned a moment ago, sklearn.decomposition has a function called PCA. I take the PCA engine. I say I'm looking for two components. So my k is going to be 2. This is in this object PCA 2D. And then I say, well, fit a transformation. Given all the data, give me a two-dimensional representation of the data using principal components analysis. There's a lot of information in this object. So this is going to also include the explained variance ratio, which we haven't really talked about too much, but this basically just says how much of the overall variance in the original data do my chosen dimensions encapsulate. And then everything else is mostly just showing things visually, and including the directions. So so for the length and the vector in this is just representing my PCA representations here. This is just drawing the arrow, its direction and its length, and so this part is drawing the principal components. I've also brought the mean to 0. So this is nothing new really. We've seen this already, but this just shows how to get it in code, especially with this function. The original data kind of spreads out mostly in this southwest to northeast direction, and indeed the first principal component is in that direction and has a very strong extent in that direction also, represented by the length of this vector. The second principal component needs to be orthogonal to the first, and quite frankly, since we're dealing with two dimensions, there's only one way that you can point in like positively in the result in the result. So that's the second principal component, which is a smaller arrow pointing in that direction. And we're literally done. If we wanted to convert the two-dimensional data, all of these two-dimensional blue dots, into one dimension, we would just project each of these dots onto the black arrow over here, this first principal component. And then the distance along this arrow from the origin on the first principal component will be the value of this data point in that direction. So if you're going to do machine learning thereafter, there's going to be a big difference between the data points down here at a very negative principal component value and the data points way over here on a very positive value of this principal component. So here's just the reconstruction I mentioned a moment ago. This is a visualization of what I literally just mentioned a moment ago. I have the original data in blue, and I'm projecting data onto the first principal component. I mean, yeah, technically it looks like it's kind of going at a non-right angle, but you have to remember that everything's been rotated. So these hash marks over here are actually at right angles to their first principal component. It just doesn't appear that way because everything's been linearly transformed again back into the original dimensions. But these blue lines kind of demonstrate this projection that I was mentioning a moment ago. So yeah, the distances from the original points to their reconstructions will capture the reconstruction error. So I convert the data down to the first principal component, and then I will then try to reconstruct the data by projecting them out into the second principal component. The amount that I lose is sort of a reconstruction error. And since most of the structure is along the main diagonal, the first principal component, the one-dimensional PCA, captures the data fairly well. Example 2 is actually using a principal components analysis and digits classification. Don't get your hopes up. Just as a warning, I'm going to come back to like why we're doing this in the first case at the very end, but don't get your hopes up for this particular example. I think I mentioned sometimes that we occasionally go into experiments expecting a certain outcome, and then you do the actual experiment, and then you see the outcome is not what you expected. And then you debug things, and then as long as everything's done properly, then whatever you observe is what you observe, and that's the end of it. And that's kind of what's going to happen here. So in this case, our decision context is classifying handwritten digits. So you have images, and the images encode people having written 0 to 9. And again, I care about accuracy on some held out test set. I also care about computational cost and training time. That's important to remember in the next few slides. And it's important also to zoom out occasionally when cameras zoom in too much. And then maybe it's going to be important to think about interpretability of features also. Okay, so it's easy to think about models that represent things in the original data space. But again, since principal components are kind of aggregates of our original dimensions, we're losing some information here. So our question is, using principal components as part of our pre-processing before we do the actual training of a classifier, in this case, logistic regression, does PCA help or hurt classification? I think you might know the answer to this question in this particular example, given all of the caveats and preambles I gave you a moment ago. But the answer to this question won't always be what we encounter here. So we're going to compare logistic regression on a few raw pixel features, and then we're going to do logistic regression on a feature matrix, which is original data projected down onto a smaller number of dimensions k, which we obtain through principal components analysis. So here is, we're loading our digits. So sklearn has all these data sets. One of them is our nice load digits data set, so we just obtain it. We get our data, we get our targets, which are our labels. We're doing classification. And then we just split the data with one single train test split. We know that this isn't really going to be enough in most cases, but just for brevity, that's all we're going to do. And we stratify things also to make sure that there's no prior problems of the labels being sampled weirdly. We talked about that in a previous module. And yeah, we have about 12,500 training samples and about 540 test samples. And all of them are 64 dimensional data. These are basically the pixels of our data. You might have heard other machine learning people call them pixels, the same thing. So here's our pipeline, and we're doing the right thing now. We're doing a pipeline. We're doing our standard scalar. So this is where we move all of the data to have mean 0. And then we just do a simple logistic regression using 1,000 iterations. And this is our baseline. And then we fit our baseline, and then we do our prediction, and we get an accuracy on the test set of 96.7%. So that's really good, and it's going to be hard to beat. Indeed, this is an easy problem to solve. So it's easy to get really high performance off the bat. So we're starting really high. Next, we're going to choose a couple of different values of k. We're going to do, we're going to take our 64-dimensional data and boil it down to 5 dimensions, 10, 20, 40, and 64. We're just going to do a grid search and see how well we do in each of these different cases. Again, we scale things as part of our pipeline. Then we do principal components analysis. So using the k components as our target, perform PCA, and then do logistic regression on the result. And this is all kind of encoded within this pipeline. So we'll use this pipeline to fit the data. So the data will be scaled, then projected down to fewer dimensions, and then trained with logistic regression. And then we will we'll use the pipe to do predictions. So the pipe knows to, again, scale the data and do principal components analysis. It'll know that it will need to do this using the transformations obtained on the training data. So again, we had a long conversation about this way at the beginning here, but we're not doing a whole new scaling and a whole new PCA on just the test set, where we're using the learned transformations from the training set. And we get our accuracy score, and then we just report the results, nothing special. Okay, here's where things get kind of silly. Our original test accuracy was 96.7, and as you can see, as we get a smaller and smaller number of components, our accuracy will drop off. It'll go from down to 96.1 to 94 to 80, 87.6-ish, and so on. To some extent, this is perfectly to be expected, and it's not a negative result. Like, obviously, this whole time we were talking about, losing information as we project our data down into a smaller number of dimensions. So we should have known that this result was going to occur. It might have been overly optimistic or naive to assume that you can remove information from a data set and then suddenly get better performance. I should mention that sometimes you do. So occasionally, like I mentioned earlier, if you have really complicated data and a small amount of observations of that really complicated data, then doing principal components analysis can avoid the problem of overfitting. And if you avoid the problem of overfitting, you tend to do better on test sets. So there are situations where the results are going to be actually positive, and PCA will give you a big improvement. Sometimes, again, the reason why I kept this in is because I wanted to emphasize that sometimes you get results of this type. This is, performances don't get better, but again, this is an easy data set. It's relatively already small dimensional, so there's not a lot of noise to overfit to. And it's voluminous enough. It's a good balance of data points n to dimensions d, so that you could learn a really good representation in the first case. So PCA is not really relevant to the problem of overfitting here in this data set, as it might be in other data sets. Again, maybe that doesn't matter so much because you want to run this thing on the smallest possible wearable computer. In the old days, like 5 years ago, I remember people working a lot on smart clothes. So like clothing that had like chips built into it, that was extremely low power and extremely low computational resources. So you're not going to have a massive model. Like, you're going to make the model as simple and as computationally efficient as possible without sacrificing too much accuracy. So this curve, which basically basically shows us what we saw a moment ago, shows that if you squeeze information out of our data matrix X, you will lose some performance on your test case or validation case, whatever the case is. But maybe there's some kind of like elbow over here where you're kind of satisfied. I've removed 44 dimensions from my data, and I've only dropped about 2 percentage points in terms of performance. maybe that's really good, right? So like a 2% difference isn't very big, but I've reduced the overall computation, naively speaking, by like a third, right? Down to a third. So that's pretty amazing, right? So this is still a positive result. Small k values are like heavy compression, and at some point you start losing more and more of the discriminative information, which results in the lower accuracy. But some of these moderate cases over here, like k components being 40, this is very close to the baseline in terms of your performance. Maybe it's better if you're removing some noise. And the closer you get to like the original dimensionality, the closer you're getting to the original data. So PCA doesn't really buy you anything. So here's like the main messages I wanted to convey. Like pre-processing will often get you better performance on evaluation. Sometimes pre-processing, like principal components analysis, does. Sometimes it doesn't. In this case, it doesn't, but it still buys us really efficient computation. And it can still be a useful tool for compression and denoising, like I mentioned, or visualization, which is going to be a main topic of our next module. And we'll actually compare PCA against another method shortly. So some final thoughts. When you apply PCA in a pipeline, you should ask, well, what is the goal? Like, am I doing PCA because I just want to take my data and project it down into 3 dimensions so the squishy human brains of the people looking at my work will be able to comprehend what I'm doing? Am I trying to just compress things into a smaller space? Do I need speed? Do I need to do regularization? So in some sense, I hinted at like a lot of PCA resembles the kind of regularization we were doing in previous modules. How will I evaluate success? Well, we didn't talk too much about explained variance ratios, but how much of the overall variance is described by each of these dimensions. That can be really relevant. Like if you look at all your small sigma 1s and 2 and 3 and 4, the singular values on the central matrix of your singular value decomposition, that kind of the proportions of each of those components represents a certain amount of the variance. So how much of the overall variance you're keeping by taking only the best k of them is an intrinsic measure of how much you're compressing. You can also try to recompute things. So I mentioned earlier, one way of looking at principal components analysis is a way of boiling data down into k dimensions and then trying to use those k dimensions to reconstruct the original matrix. I get x hat. What is the difference between my original data and my reconstructed data? I have something called the Frobenius norm, which is essentially very similar to a 2 norm. That's the difference, the squared differences. So if this value is very small, I can reconstruct the data. I've done very good lossy compression. I haven't lost too much. And downstream tasks, can be important. Like maybe doing PCA with a very small value of k results in a drastic loss in accuracy or F1 on a validation set, or maybe a test set, but validation really. And this can be a sign that PCA is overly, you've been overly aggressive with your PCA. And again, I mentioned this several times, only fit PCA on the training data. If you are fitting PCA and finding those dimensions using test data or validation data, then that's leakage, you're cheating, you're using information that you shouldn't have yet to determine the optimality of these dimensions. But once you have those dimensions, then you just take them and you use them as if they're just a transformation, and you transform like a function, and you transform your test data using those the principal components you've already computed. A good rule of thumb is to choose a value of k that's as small as possible, as long as you explain as much of the variance as possible. So choose a k such that the proportions of the singular values are at least 90 or 95% of the overall sum of the diagonal. Or in other words, broadly speaking, you've explained 90 to 95% of the overall variance using only these k dimensions. Also choose the smallest k possible such that any degradation in your downstream performance on the validation set is no more than some minimum cutoff. Losing 2% of performance for gaining 2/3 of the space back might be acceptable to your deployment. So I'm not going to go through all of this. These are a lot of links to sort of PCA and its descendants, but PCA shows up a lot in image compression for face recognition. So, face recognition is one of those computer vision tasks that is sort of foundational to the field, and image compression methods sort of learned a lot from PCA, and they use things called eigenfaces, aligning faces as linear combinations of principal components, which is kind of cute. This goes way back to before any of our times. Genomics and population genetics. So like, genomics, like genomic data is huge, populations are huge. So, compressing the data into a smaller number of dimensions that still captures a lot of the useful information is always important. And then recommendation systems similarly can be very high dimensional, and factorizing the models for things like ratings or making predictions about what a user is going to click on. This is becoming increasingly icky year after year. When I was a student myself, recommendation systems were perfectly interesting and cool, and no one could use them for nefarious purposes. But regardless, like a lot of things, things can be used for good and ill. Anyway, regardless, you're going to make recommendation systems for good purposes, like optimizing resources in an effective way in a hospital. So a PCA is a way to kind of get recommendation systems that encapsulate a lot of useful information. There are some other kind of generalizations. There's something called kernel PCA, which is a PCA space defined by a kernel. And this reaches back to one of our previous modules on kernel spaces. There are other generalizations to deep autoencoders and variational autoencoders. We haven't talked about neural networks too much, but these are the topics of these papers. So again, look into them, and a lot of these are based on reducing the dimensionality of data, using neural networks as an alternative to principal components, but using a lot of the same underlying techniques. And spoiler alert, PCA is often used within the context of modern visualization methods like TISNE and UMAP, which you're going to see in the very next module. And again, papers available for you to read about them here. So quick checks for you. A very small number of questions given all of the content that we just went over. There's a lot of mathematical detail that we talked about here, and it's, I think, super interesting, and it's wonderful that you can come to the same conclusions from many different angles. That just reinforces the preeminence of PCA, at least in linear dimensionality reduction. But regardless, there's only a small number of high-level concepts we really touched on today. So yeah, quick check for you at home. Here are the references. As usual, it's been a pleasure. See you next time.